Welcome to Advanced Reverse Engineering. This homework, most of you had completed it after I went ahead and updated the due date, which is great. But in case you haven't completed it, or you want just a little extra time to take a look at it, it's now due Friday night by midnight. So please get it in by then, and that will be good. Find main. We've talked about this. I think you all know what you're trying to do. I'll just say be sure you get the address correct. Do some tests by hand. Maybe build a program and look where main ends up, and you should be good. So let's talk about computing ethics. So we've talked about that previously, but I want to talk about it again and put it in maybe a little bit different context. So I suspect some of you belong to professional societies. You may belong to the IEEE or the ACM or any of a number of others. Professional societies often have a code of ethics that they expect their members to be held to. And the ACM is not unusual in that regard. They've had a code of ethical conduct for computer scientists since 1992. However, they revised it in 2018, and we'll talk about why they decided to do that. The new Code of Ethics, you might want to have a look at it. It's been used by a couple other organizations, in particular the International Federation of Information Processing, or IFIP, has adapted ACM's code to create its own. So it's being used as a template for others. So it's worth taking a look at. We won't go through the whole thing, but we'll just take a look at some of the highlights of it. The general principles of the code, and you can read the whole thing at that link, but the general principles of the code are that as a member of the ACM and a computing professional, you should contribute to society and human well-being. Okay? Now, what does that mean? That means that you should do work that makes things better for as many people as possible, that makes the world a better place for the rest of us all to live in and for future generations to live in. And that's kind of a worthwhile and fundamental principle of a lot of ethical systems. And we can everything else is sort of an addendum to that. That's the main overriding principle. You as a computing professional should use the skills and the knowledge that you have, what you're learning here at Tech, and what you learn in your career to make things better. Not just to make things, but to make things better. And part of that is avoiding harm. So you have to acknowledge, you don't have to, but you should, this is ethics, right? You should acknowledge that the actions you take as a computing professional in terms of writing code or writing reports or doing whatever it is you're going to end up doing in your career affect a lot of people. There are many stakeholders, right? There's the people in your company, there's your customers, there's the people who may be funding what you're doing, there's people who may not be any of those, but who may nevertheless be affected. They could be users of your software, or they could be people whose lives are impacted by the use of your software. We'll give some examples in just a moment. You should try at every stage to avoid harm. You should be honest and trustworthy, right? If you're not in scouting, you should still be honest and trustworthy anyway. You should be fair and take action not to discriminate. And so to be a little more clear about this, not discriminating requires positive action. Because there are systems that exist, that are set up, that may have some forms of discrimination baked into them. And if you come along and just sort of pick up this tool and march forward with it, you may not be aware that there is some discrimination baked into the data or into the design or into other aspects of it. You should take that into account, and you should try to be sure that the work that you do right? When you pick up this tool or you pick up this data, you should take positive action to try to be sure you're not discriminating against groups when you do that. Respect the work required to produce new ideas, inventions, creative works, and computing artifacts, especially now with the advent of these generative AI systems, right? That is working its way through the courts. It's going to come to a head. I don't know how that's all going to shake out, but you need to be aware that other people have expectations about their ability to control the work that they produce. Respect privacy and honor confidentiality. So there's a collection of case studies available online at that link to help you understand how you would apply the ACM's new code of ethics. It's worth taking a look at. This is part of the preamble of the ACM code, and there's a lot going on here, but basically they say the code is not an algorithm for solving ethical problems. There isn't one, right? We don't have an algorithm for solving ethical problems. We have a series of different approaches for how you might engage in ethical decision making, and we'll talk about that in a moment. But we don't have an algorithm that turns the crank that says A is good and B is bad. The code serves as a basis for ethical decision making, and when you're thinking through an issue, you can find that there's lots of different things that you have to take into account, and sometimes they can even seem to be in conflict. Questions related to ethical issues, try to engage in thoughtful consideration of the ethical principles. Try to understand that the public good is the paramount consideration. Right? There's a lot of social contract theory behind the ACM code. The entire computing profession benefits when ethical decision making is held to account and is transparent. And that's true. You want people to look at the computer science world and say, I think those are good, well-intentioned people who are trying to make life better for all of us. You don't want them to look at it and say, that's a bunch of shady people who are just out to make money, who are stealing other people's hard work and using it to further their own careers. You don't want that, right? All right. So, you're considering doing something. You should ask yourself, why am I considering this action? Right? What's my intent behind this action? I'm going to write a piece of code, I'm going to write a report, I'm going to release a product, whatever I'm going to do, what's my intent? What are the consequences of this action to myself, right? To others, and you should try to be as broad as you can be, right? Who are the people who will be affected by whatever it is that you're doing, right? You don't just think, I have a duty to my stockholders to generate value for by selling this to some customer. You have to think, how will the customer use it? Who else in the wider populace will be affected by it? You think about the short run and the long run, right? What's the immediate impacts of this, or what do I think they might be? What are the impacts in the long run? Now, can you get all these answers right? Of course not, right? We're living in a world of imperfect and incomplete information, and you may fall prey to the universal law that every action has unforeseen consequences, and that's fine, right? We can look back and we can ask questions about your intent, right? That's why intent forms so much of the law, right? We try to be sure that that your state of mind when you were doing something is what we're looking at or evaluating when we try to decide if you've committed a crime. Not always, but most of the time that's what we look at. And so the idea is, do the best you can. And if it's something that you're concerned about, that you really have some concerns about, document what you did. Say, I've thought about this. I talked to company lawyers. I talked to the company ethicist. Some places do, in fact, have them. And I gave consideration to this, and here's the decision that I made, and here are the impacts that I think will happen, because you may someday be called to account for why you took some action. Is the action legal? Well, legality is important, certainly, but legality is not the same thing as ethical. The legal can be unethical, and the illegal can be ethical. We have a whole body of literature to fall back on for examples of this. We have a whole world of examples around us to go and look at. You have to make the decision within a legal framework and also within an ethical framework. And those two things can be in tension, right? They can come into tension with one another. Some of you it's entirely possible that some of you will wind up in a job where this kind of concern is sort of baked into your day-to-day actions. And that doesn't mean you get to be absolved of it because the organization is doing these things and because these things are regarded as legal. It doesn't absolve you of your duty to try to act ethically. Is this action consistent with ethical codes I've agreed to? Right? If you're a member of the ACM or the IEEE or AAAS or any number of other organizations, or you're a student at Tennessee Tech, you have either explicitly or tacitly agreed to some set of ethical guidelines that you'll agree to abide by those, and your actions should be, whenever it's possible and reasonable, consistent with those ethical codes. Does that mean those ethical codes are correct and they address every situation correctly? No, right? So you have to also be consistent with your own moral code, and you've probably accumulated a moral code, like most of us do, somewhat randomly by walking through the world and bumping into things and making decisions about what you believe to be right or wrong. That's fine. That's how we learn almost everything that we do learn. That doesn't mean that code can't evolve and change. It means that you have a moral code, and to feel good about your own actions, to feel good about yourself, which is an important value, you should try to act consistent with your moral code, or maybe reevaluate it and understand why the moral code that you've adopted may not be the most ideal. And then, how would I justify this action to others? When I'm called before Congress and they ask why I did this, I will give them my explanation and hope that that will be sufficient. How will you justify your actions to other people? How would you feel if what you did were reported on the papers, or a 20-minute video on YouTube, or wherever these things get reported? The revision of the ACM code arose because of the ethical crisis in computing. So you can read about that. There's a Boston Globe article there from 2018, and there was a perceived ethical crisis in computing. And you can look back on this and say, well, I think this was widespread, or maybe I don't think this was that widespread, or this was significant, or this was not. But I can tell you that a lot of people who looked at this very closely said, yes, there is a problem with the people who are computing professionals. There's a problem with them not acting ethically, either because they don't know how to act ethically, or because they don't consider the impacts of their actions, and something should be done about that. And one of the things that was done was a revision of the ACM code. Other things have been done as well. And this arose from two primary sources. You won't be surprised to see that AI is mentioned on here. As AI has grown over the last decade, it's bumped into a lot of areas, and it's had impact on a lot of people beyond the people who built and trained the AI, beyond the people that are the companies that sell it, beyond the people who are the users who make use of the tools. It's impacted many, many, many others. AI is used in criminal sentencing. So it impacts the lives of people who are sentenced in the criminal justice system, a large number of whom every year are discovered to be innocent. So you need to factor that thought in, right? Criminal sentencing is often based on a pool of data. That data may be the result of a biased system. And so that data has bias built into it. And so your AI decision making also has bias built into it. The same thing is true for loan approval. The same thing is true for policing. If we're telling police where to go or who to pull over or where we think the crimes are going to happen. And AI does all those things. We need to be aware that the prior history of highly biased policing affects the data that we use today. And if we base our decisions solely on that data, we say, I'm going to be unbiased and just look at the data, we are looking at biased data. We'll come back to that in just a moment. Okay. The second big issue was violations of personal privacy. Privacy is still a value that people people hold dear, and even if you think privacy is dead, that privacy doesn't matter in the modern age, you're wrong, because privacy matters quite a bit to a lot of people whose lives and livelihoods may depend on privacy, and to companies which have many of the same concerns and whose business depends on privacy of the data they collect and their trade secrets. So if you're curious about what I meant when I was talking about algorithm bias, there's an excellent article here in Vox, why algorithms can be racist and sexist. Even when we think that data has been carefully curated in a way that has eliminated bias, we have to remember we're sampling the world. That we as imperfect human beings are going out into the world, conducting experiments and collecting data. And the data that we collect, because it's only a finite sample of our infinitely diverse world, is going to have likely to have some kind of bias baked into it. And it can be systematic bias. Maybe we're sampling from a system that already has bias built into it, and so the data we get contains that bias. Maybe we're sampling in a way that incorporates a hidden or tacit bias into the data. We send people out to survey people, to talk to them on the street, let's say, and collect information. But because of that person's own personal biases, they don't have a fair sample, or they don't talk to everyone. They talk to people they're comfortable talking with. And people who are uncomfortable talking to them for various reasons don't talk to them, and we don't get their data. So there's lots of ways in which these things can become can have biases baked into them, and you have to be aware of that. Privacy is a fundamental human right. It's in the United Nations Declaration of Human Rights. The U.S. has ratified that back in 1992. But of course, since we're the United States, even if we agree to it, it doesn't really apply to us. So you can see the 2004 SCOTUS case there, where we say that the declaration, which we ratified, informs but does not impose obligations under U.S. law. Doesn't rise to the level of a treaty or to the level of U.S. law, and so we can look at it if it's convenient for us to do so. If it's not, we'll set it aside and make a decision independent of that. A number of Supreme Court cases do recognize a right to privacy as a unifying principle from the Bill of Rights. There's, I can't remember who said this, but it was Supreme Court Justice who said the underlying principle of the Bill of Rights is the right to be left alone. And a number of things have come out of that. The notion that there are quote-unquote penumbras that come out of that hint at a right to privacy, and we should try to honor that, form the basis for Supreme Court jurisprudence for a very long time. Some of that has been set aside recently, but there's still a very large pool of Supreme Court case law that recognizes a right to privacy. And this comes down to the idea that the U.S. government needs a compelling reason to invade your privacy. They can't just walk up to your house, kick the door in and go rummaging through your things. You have an expectation of privacy, and the police need to establish a reason to do that, right? It could be exigency. They think someone is being held hostage in your house, right? Maybe you're holding someone hostage, or maybe somebody has swatted you. But the police believe there's a reason why they need to act now. They have probable cause, right? You've been, you haven't just been acting shady, but you've been doing things that have led the police to be almost certain that they need to get into your house now to prevent a more serious crime, or they have a warrant, or they have some other court order that allows them to tap your phone or invade your privacy in some other way. So is privacy dead? And I think the answer is no. Companies want privacy to protect their data. Their data include trade secrets, and the data can include data about you. As Facebook and Twitter and others collect data about your behaviors and what you're doing and what you click on, that data is worth money. They sell that data. If that data is available to everybody, then they can no longer monetize it. So they want your data. They want others not to have your data unless they sell it to them. And so they want to keep that data just between you and them. Companies sometimes make their data available under license agreements that require a licensee to protect the data. If Facebook turns around and sells data to you, they may say that you're not allowed to publish that data or give it away, because that undercuts their ability to further monetize that data. And data protection measures that they take are really sort of the same kind of data protection measures you would apply more generally to protect individual data, right? If you have a system where you can keep data secure for a company, then you probably have a system that can be equally applied to keep data secure for an individual. And you don't have to be trying to protect your data for nefarious purposes, right? There could be people, and there are people in the world who are persecuted, sometimes very seriously, sometimes are killed, either for an accident of birth or for very deeply held beliefs that do not harm others. And in both those cases, privacy is very, very important. It may be the difference between a life where you can be free and contribute to the world and a life where you're imprisoned or killed. And that's very, very serious. To pick on one argument here, there's a common argument in favor of government surveillance. If you've got nothing to hide, you've got nothing to fear. And that presumes a couple of things that may or may not be true. One is that the people who want to surveil you share your values. Well, they probably don't, right? I mean, do you want to surveil all of your neighbors? You probably have other things to do, and you probably don't want to do that, don't think you should, but these people think they should, so they almost certainly don't share your values. And surveillance agents don't always act in good faith. Sometimes the answer is, let's collect everything, and then we'll look for a crime in it later on. So that has absolutely zero credibility as an argument. All right, so that's enough of that. Be aware of these issues. Think about what's going on. Believe it or not, you're learning some techniques by now would allow you to do some pretty nasty stuff, and you need to think about what you're going to do. But for right now, let's think about how we discover control flow in a assembly program, or in any program. We talked about this before, so we're going to do a quick review of it. A flow graph is just what the name says. It's a graph of the flow of the program. Data flow? No, control flow. It says how are the instructions in the program, in what order are they executed? What is the algorithm that allows them to execute? And we try to, for our purposes here, break things into two different kinds of nodes. So a node could be an instruction, or it could be part of an instruction. Because the two nodes are going to be a function node, where we're going to say, I'm going to take an action. I'm going to make a change to the state of the machine, and then I will flow on to the next instruction. Or it's a predicate node where we say I will not change the state of the machine, right? No side effects, but I will evaluate the state, and based on that I will flow to one of potentially two different locations. We can combine these function and predicate nodes like you see on the far right to make something like the little sequence you see there, a while loop followed by the function f, the while loop, while not p, do g, and then finally when that predicate fails, we go and we do f. A proper program is a program with a single entry point. That is, control enters our program at a single place. And notice when I say program in this context, I could mean a function within a larger program. I could mean a block of code, a basic block. I could mean anything that's a sequence of instructions to be carried out. And that sequence of instructions will be a proper program if control flow always flows into the same place. We don't just jump into the middle of the block of code. Okay, we enter at a defined point. Maybe it is the middle of the block of code, but that's where we always enter. Okay, so we go in one place. We always start at the same place, and we exit. We exit to the same place. And notice I said to the same place, not from the same place. If I write a piece of code and it's got 18 returns in it, those returns are all going back to the caller, so they're going back to the same place. It's really a single exit that I have broken up in this way, but it's a single place that control flows out of our program and to a single destination. In addition, to be a proper program, you need to have no trap nodes, places where you go and just get stuck and you can't get out of them, or unreachable code that you cannot get to from the entry. And as long as you don't have those two things, and you have a single entry and a single exit, you can be a proper program. Once we've defined a proper program, it represents we can think of it as representing a single function, right? We enter at one point, state is transformed according to some rules, we exit at some point. The pair of the initial state and the final state really define what the function itself does. And we have everything we need to know. That doesn't, control doesn't suddenly jump out of it somewhere and run off somewhere else. It flows through that sequence of steps to the end. Over on the right, there's some code from the Linux kernel. I like pulling code out of the Linux kernel. I really do, because there's a lot of interesting stuff in there. And this one is a good one. It has a great comment in it. What lock protects these flags? Who knows? I don't know. Apparently the person who wrote this doesn't know. And is that code a proper program? Well, we can do a number of things to figure it out. We could stare at it and think hard, or we can just draw the flow graph, which we did at the bottom. And you can see at the bottom that it is in fact a proper program. Single entry on the left, single exit on the right, and then you can see there's a path straight through it. Right, each node for each node, I can draw a path from the entry to the exit that contains that particular node. In this case, it's super easy. I just draw a straight line and I get them all. Now, in particular, this one has what we would think of as a proper sub-program. So once we've talked about a program, we can talk about a sub-program, and it's like a subset, right? I can draw a box around this, and I can capture a proper program inside that box, right? So I cut two arrows, one going in, one going out. That's my single entry, single exit, and everything in there is reachable from the entry, and I can reach the exit from everything in there. So I'm good. That's a valid, proper sub-program, and it is itself just a proper program, just like a subset is itself a set. And so I can think about taking a big program and decomposing it into sub-programs. Or I can think about taking a collection of sub-programs and building up a larger program from them. So prime programs are an interesting idea. Prime programs are are programs that contain no proper subprogram of more than one node. It's very analogous to prime numbers. And the primes are over there on the right. So the first one is a little sequence. If I try to draw a box around something, either I'll get the whole sequence or I will get a single box, which is not allowed. And so I can't do any better than that. I can't break that down any further. Same thing for the if then else. Same thing for the while do below it. At the bottom, that thing is not a prime because I can draw my box around G and F, and that's a proper subprogram. Therefore, it's not a prime. It is a composite program. You can prove there's an infinite number of prime programs. That's kind of neat. And you can prove some interesting decomposition theorems about software in terms of primes, right? Every program can be written as a composition of a set of primes, and unlike the integers where I have to have an infinite number of primes to construct all the integers, I can get away with a finite number of primes to construct all the programs. That's kind of neat. That's sort of the same situation we have in in predicate logic, where we have a functionally complete set that could be and or not, or it could just be NAND. So a structured program is a program composed using a fixed finite basis set of program primes. And we think of program primes as program structures. If we go back, we'll see we have a sequence, we have an if then else, and we have a while do. Okay, those are all things we recognize. Those are all common program structures. There may be others, but we set our basis set and we build our programs from that. So an interesting question is, can every program be written as a structured program? Will there be a time when we have to fall back on using gotos? And the answer to that was provided by the proof of something called the structure theorem. So the structure theorem says every proper program is execution equivalent, meaning it does the same things and in the same order, to a structured program. And there you go. Every proper program is execution equivalent to a structured program. That's great. What is that structured program? Well, it's a program composed from a basis set. Could it be any basis set? Well, for the purpose of the theorem, we picked one. We say you can use while do, if then else, and sequence. Those are your three structures. You won't need any more. We can get away with just those three. In fact, we can get away with a smaller set than those, but we begin to get into some pretty esoteric types of control structures. We can do this, but we need a little bit of additional information to make it work. We'll use the original function and predicate nodes of the original program, but we'll add a tiny bit of additional information. And that information is a counter of a certain number of bits. And the number of bits is given by that little thing there, the supremum of the log base 2 of the number of nodes. Don't worry about it. Just assume there's a counter. It'll make sense in just a few moments. So let's get started. The proof of the structure theorem is a constructive proof. Given a program, we tell you how to construct a structured program, and you can see the structured program. The proof has a lot of different moving pieces in it. We won't go through all of that. We'll just go through the important parts of the construction so that you know how to take a program and structure it. Step 1 is the hardest step. We have to assign every node a number. I mean, oh my goodness. We have to assign the exit of the program the number 0. Every node gets a different number. Typically, you just count up, right? The first node on entry gets 1, then you assign all the others numbers. If it's an assembly program, you might assign each instruction its address, right? That's a perfectly fine number. Just give it the address. Give the exit 0 again, and you should be good. So we want to do this. We divide up the operations into classes, and you can think about different instructions like jump and loop. And in these cases, you may have something that results in an odd sort of control flow, like jump to the contents of EAX. How do we address that? Well, that's a little bit more difficult to address. We don't necessarily know what EAX is without either symbolically executing the program or doing some other kind of deeper analysis. And so we have to treat that as a potential exit from the program, and that may complicate our analysis. But you know, we won't worry about that for right now. What we're going to do is look at the functions and the predicates that are present, and we're going to do some things with them. So now we've numbered all of the nodes, and for each function predicate, so you see I there has this function f, whatever that is, and then it flows on to next, whatever the next node is in your flow graph. We are going to transform that into the little sequence that does f and then sets the counter to next. Remember, the counter is that additional piece of information that we get, that we were required to have by the structure theorem. We set that counter equal to next. And that little sequence can be thought of as a little function, f sub I in this case. Right? It does makes a transformation of the state. It has the entire machine state plus the new counter, and it makes a change in that. It does whatever change f does, and then it sets c to next. For the predicate nodes, we do sort of the same thing, except now we have two places to consider. It might go to a location when it's true, and it goes to a potentially different location when it's false. We're going to transform that into an if-then-else, where we set the counter to the address where we go when it's true, and we set the counter to the address where we go when it's false. That is now a complete if-then-else. We can think of that as a single function node as well. Once we have this, we do this for every single numbered node in the program. And now we are going to combine them. So if you look over on the right, you'll see that we initialize our counter to be 1, because we've numbered the first thing on the entry line as 1. We come into the program while C is not 0, right? C will be set to 0 when we encounter the exit. So while C is not 0, we then figure out which node to do, F1 or F2 and so on. We perform that node, we go back around, we check C again, and we keep going until C is set to 0 to terminate. This loop essentially emulates the original control flow of the program. Let's see that in an example, and I think some of this will make a little more sense. So here's an example. This is an example from Exon XOff flow control. Exon XOff flow control is a software flow control mechanism. It's used for RS-232 serial links and other kinds of serial communications. It's used in some protocols that are out there. Sometimes you have hardware flow control, where there is a piece of copper that tells the system that you can transmit, or you have to stop transmitting because my buffer is full. In this case, characters are transmitted back from the receiver that says stop sending and resume sending. The stop transmit is X off, right? X off says stop transmit. X on says resume transmit. And these characters are 11 and 13, hex 11 and hex 13, and they also work in your terminals. So let's go over here. Let's get a little terminal. And some of you may have encountered this and not known what was going on. So here's my ls-l, and I accidentally push Control S. So now I push Control S, and I would like to do some more stuff. I would like to cd to etc ls. What? Nothing's happening. What? What? Nothing's happening. Nothing is happening, not because the terminal is dead, but because I have hit Control S, which is the stop character, until the terminal has stopped transmitting data to me. But that data is still there. So if I hit Control Q, it will resume, and watch this. Hit Control Q, suddenly I get all the stuff that had happened before. So if you accidentally hit Control S, and nothing is working, type Control Q just to see if that's what the problem was. So that's Exon XOff flow control. And then over here is some code that comes out of a program that was used to communicate with an Apple laser writer. Apple laser writer communicated over a serial line, and it used Exon XOff flow control. Still pretty common today, so there you go. And here's how it works, right? We come in up here at the top, And we've got some data to send. We have some length and a buffer of characters. And we set up an index and a character to send. And while we haven't sent everything, or once we've sent everything, we return the number of things we sent. But then we send a byte over the serial line. We increment the index. We read a byte coming back to us over the serial line. We check to see if that byte is the X off byte, and if it is, or sorry, if it's not, we go to top and we send another byte, and we just keep spinning and sending bytes as fast as we can until the buffer on the other side fills up. And when it fills up, in this case with the laser writer, which is having to do a whole bunch of work, right? A laser writer is getting a data sent to it, and it has to print that on a page. And the rate at which we can send data is way slower than the rate at which we can print a page, right? And because the printer has to it has to ionize, you know, atoms of the metal on a disk. It has to pass it over, you know, fine plastic. It has to you know, charge a piece of paper. It has to, you know, pass the paper over the plastic. It has to melt the plastic with a fuser. All that stuff has to happen. Paper handling has to happen. And so the buffer is going to fill up, and it's going to say, don't send me any more until I'm done with this page, and it will tell us to wait. And so we hit wait down here, and then wait, we read a byte, and while it's not X on, we go back up to wait. Otherwise, we go back up to the top. Is this a proper program? This should not be a complicated thing for you to figure out, right? You should be able to look at it and say, well, I know immediately that this is a C function, and I know C functions start here at the top, so it's got one entry. I know that I only saw one return right here. I don't see anything down here about getting out of it. Only way to get out, and that's this return. Okay, so it's got a single entry and a single exit. Is everything reachable? Well, we're going to do those because we come in. We're going to do this stuff. And yeah, everything is reachable and you can get out of everything. So it's a proper program. Is it a structured program? Well, it's not obvious that it is. And maybe it's not obvious that it's not. Right? Let's build a flow graph. So we can build a flow graph. Here's our flow graph. And is it a proper program? Is it a structured program? Notice we have the labels in here. Here's top, and here's wait. These little merge points. We would add our phi functions to them if we were doing some other work. So let's structure this, and we'll get started by doing the hardest step, which is we'll number everything. And so we number the first node on the entry 1. We number the exit line 0. Doesn't matter what we number everything else. I'll just, you know, number them as I see them. So 2 and then 5 because I wanted to throw you a curveball. 3, 4, 6, 7, 8, and 9. Fine. Doesn't matter how the order of numbers works. It doesn't even matter that they're sequential. I could have numbered them, you know, 100, 200, 500. Be fine, right? The trick is I want the exit line to be 0, and I need to know what the number is for the first thing I encounter on entry. And typically I'll make that 1. But if it's not 1, I just have to know what it is. So now once we've numbered them, we build all those little proper programs. For every node, we build a little sequence of it. So let's take a look at one of these. Let's take a look, for example, at 4. So at 4, I increment the index, and then I set C equal to 6. And if I go back, I will find that sure enough at 4 I increment the index, and then I flow on to 6 where I set CH equal to the byte read. Great, so we have all of these. So that's a lot, but we can plug them all together in our big structure. We initialize C to 1 because that's where we start. While C is not 0, we see what C is. Initially it's 1, so we'll do this and set C equal to 2, go around, it's not 0, so we'll set C equal, we'll satisfy this predicate, we'll do CH equals 0, and now we'll set it to 5, we'll go around, and now we're down here. And we'll keep iterating that way, and basically we'll run the original program using the counter to tell us what we do next. And it's a fairly long structure. In fact, it's 2 slides long. Now, if we go back and think about what's happening here, and let's go back to the top. Here I have C equal 4. So what that tells me is set the counter to 4. When I go around, I'll do this. I will increment the index and set C equal to 5. Well, that means that the effect of setting C to 4 is that I'll do this next. Well, I might as well just take these 2 nodes and substitute them in for 4. And if C equals 4 only appears once, and it looks like it does, then I can do that. I no longer have to consider C being set to 4, right? This gets moved up here. It eliminates this branch. I might try that for 5 down here, but look, 5 is referenced here and it's referenced here, so I have to duplicate some nodes if I wanted to do that. That could be okay, but if we just focus on the ones that appear just once, that are referenced just once, we can wind up with something like this. So by substituting everywhere that a node is referenced only once, I wind up with just 3 structures. This one, and this one. And these 3 structures capture 3 important aspects of the control flow. Structure 1 down here captures the initialization. Structure 5 captures the normal flow of the program where I send a byte and then I look for the XOF character. And then 8 captures the place where I find the XOF character and I wait for an XON. If I put those in the context of that larger program, I still set C to 1. I still check to see that it's not 0. But now I only have 3 cases to consider. 1, 5, and then the only remaining case is 8, so I don't really need a predicate for it. And this is a little bit better to look at. There's some more structure exposed here. But there's still more we can do with it. So up here at the top we have 8. So if C is 8, we come in here. We then do this little predicate. And we might set C to 8. But it was already 8, which means when we go around, we'll come right back here. And we'll keep doing that until finally this is not true. We come out here, set C equal to 5, and then we go somewhere else. We can turn this into a loop. When it's exactly the structure, I can rewrite it as what you see down below. So I come in to 8, then I do 9. If it's true, I set C equal to 8 and go around again. And if it's false, I set C equal to 5 and go on. Well, setting C equal to 8 is redundant. I don't care, right? Because that's already what C is. So I might as well get rid of it. Discard the redundant node. And now, look, I just have this do while structure followed by setting C equal to 5. We can play the same game for the larger structure, for structure 5, right? Because we've eliminated, so remember, we eliminated one of the C gets 8 nodes, and there were only 2, so now there's only 1, and we can substitute for it, and now 8's gone entirely, right? Here we've dropped 8 directly into where it was referenced in structure 5, and there it is. Notice that on both branches of this if then else, at the very end, we set C equal to 5. We do it up here as well. Let's factor that out. So now it's taken out of that and it's just over here. So we have 2 possibilities. We come and check this. If it's not true, we do all of this and set C equal to 5, which means we go around and do the same thing again. And if it's true, we come over here, return the index, and set C equal to 0, which terminates our little program. We have another loop, right? Coming in at 5, setting it to 5, going around again. We can make that loop explicit, and here it is. So now we come in, we do all of this, we do all of this stuff, and then we go back around to 5 again, or we come out and set C equal to 0. Well, actually, we've pretty much captured everything in here. The thing that we're missing now is initialization. And here it is at the bottom. So this happens, we set C equal to 5. We might as well plug this big structure at the top in where it says C gets 5. And when we do that, we wind up with this final structure. And this is all of them, which means I can throw away the loop and all that other stuff we had before. I don't even need the counter anymore. It's been completely eliminated. And I have a structured program. Right? Do I really have a structured program? Sure I do. Here I have a sequence. Here I have a do while. Here I have an if then else that contains a do while that is part of a sequence, right? This sequence and this if then else together form a larger sequence. I have a while do, right? So here's a while, do this, and go around, and while this is true, continue to do that. That is part of a larger sequence. I do initialization, then I do the while do, and then I return the index. This whole thing is a structured program. It's a larger program built from these prime structures. And we can analyze it that way as well. Let me step back one. I can go in and analyze this do while and figure out something about it and use that information then to analyze the containing structure, and I can work my way out like this. I can analyze this sequence and then I can compose it with what I get from analyzing this if then else, and then put that in the larger do while, etc. So it gives me a disciplined way of analyzing it. And I don't need every rule in the world. I just need a rule for how to handle, in this case, do whiles, if then else's, while do's, and sequences. And once I have those, I can analyze programs. Here's our new implementation based on the stuff we wrote. We just read this straight off, and you can see, right, nothing super special here. It looks like any other normal structured C program. We can compare the two. An interesting thing about the one on the left and the one on the right is that the one on the right has some additional structure to it, which allows the compiler to do more optimization. So typically the one on the right is going to run faster than the one on the left. The one on the left, the gotos break up the ability of the compiler to do certain kinds of analysis. Those are gone on the right, so the compiler can make assumptions about control flow, and it should be correct. So structured code, good. Is the unstructured code, is that code on the left bad? Just different. Just different. The original flow graph was already structured. It may have looked like it wasn't, but as we peer into it, we can see that sure enough, there's a do while, which is part of an if then else, which is part of this thing right here, right? This is a sequence that comes in single entry here and single exit there, and does this as part of this larger sequence as part of a do while, as part of a while do, and that's part of a larger sequence. Great. There's homework. The homework is due on the 9th. And for this homework, you're going to do some live variable analysis. So let's stop for a moment and think about what live variable analysis is. I want you to just take a look at the code over here on the right, and let's assume that the return is going to hand us back RAX. We know that. So we'll say RAX is live immediately prior to this line. And we always have to say live prior to or after some line of code, right? The line of code runs to its conclusion and terminates and does something, and that may change state, and then we talk about things being live or not live in that pre-state or that post-state. So we're going to assume Rx is live immediately prior to this return. So we take one step back and we see that we are popping RBX. That is overriding the prior value of RBX. So we know at this step right here, prior to this pop, that RBX is not live. So if it was in our live set, we take it out and throw it away because it's no longer live. It got overwritten. We take another step back past this move. What does this move do? It overwrites RAX with the contents of RBX. And so we know prior to this move, RAX is not live, right? Because whatever value RAX has at this point prior to the move will overwrite it. What will it overwrite it with? It'll overwrite it with RBX's value, so RBX is live prior to this line. So we're beginning to develop a way of dealing with these. We're saying, well, if a register is read, then it must be live immediately prior to that line, at least syntactically live. And if a register is not read, but it is written, then it's not live. What if it's both read and written? Well, you know, we throw it out of the set because it's written, we add it back because it's read, so it doesn't change. And we just walk our way back through here. Now, a few things of interest in here. We have a call. What we do is this call. You're going to ignore the call. You'll make use of what you're told by the Capstone library. So we'll cover that in just a few moments. And you'll be able to walk back through and deal with all these things. I want you to do the analysis assuming the following registers are live at the return: 12, 13, 14, 15, RBX, RSP, RBP, and RAX. Why those? Well, RAX is obvious, I think. RAX is in this list because RAX is the return value. RSP and RBP, what about those? Those are important to the outer context, right? RBP has your caller stack frame. RSP is the stack pointer. Those are certainly live at the end, or we should at least consider them to be live. That's why we have to restore their value at the end, because you know, if we've messed it up, we might mess up the caller. So we think of those as live. These three right here, I think it's pretty obvious why we think of those as live. What about these in front? 12, 13, 14, 15, and RBX. Those are registers that a called function should not tamper with, right? If I want to use RBX, I need to push its value and then pop it at the end so I don't mess it up. And in fact, that's what the code we see over on the right-hand side does. It pushes RBX, uses it, and then pops it at the end to restore it. Okay, so these are the registers that have to be preserved by the caller. Okay, these are, sorry, the callee. These are callee preserved registers. They are registers that have to be preserved across function calls. So they have a meaning in the outer context, and we should always consider them to be live at return. So given this, given these 8 registers we will consider to be live, we want to walk back and you know, start with this set, but then work our way back and compute a live set for each one. And that will look like this. All right. Oh, sorry. That will not look like this. We'll get to what it looks like in just a moment, but I do want to mention, how do I figure out what registers are read and which ones are written? Now, we covered this in lecture 16, but it was a real quick, here's how you do it, and then we moved on. And now you've actually got to do it. So let's take a look. So we go into a particular instruction. So in your, this is in your Capstone process, you'll get a CS instance or instruction instance. In this case, it's inst. And you'll do regs access. This is a function that will hand you back a pair consisting of the read and write sets of registers. And these are numbers, right? The registers are identified by numbers. Capstone works on a whole bunch of different platforms that have different register names, and so it manages them internally by number. You don't want numbers, you want names, and so we're going to convert them to names just as follows. So we'll use a Python list comprehension. We talked about it before, but in case you don't remember, we are going to take each reg in regnums. So reg is a number out of regnums. We convert that to register name by using regname, which is a handy helper function provided in the instance. We pass it that little number, and it hands us back a string that identifies the register. That string might be R RAX, or it might be EAX. Oh my goodness. Well, EAX is another name for RAX, or at least for part of it. So that's going to mess up our analysis. Well, we're going to fix that. We have a function we'll see in a moment called normreg, and what that will do is that will convert EAX into RAX. So we won't have to worry about that. So we do this and we get the names of the registers that are read and the names of the registers that are written. We might also get the flags in this, and that's okay. And I don't mean we'll get ZF in here. I mean we'll get the flags, the name of the flags register in here. You'll see that in a moment. And then we can debug and write them out if you want to see them. You'll get the XMEM registers in here. In class, I said I want you to just focus on the primary registers because it used to be the case that Capstone wasn't great about that. It looks like that's all been taken care of, so you should be able to get all the registers now, and it should be just fine. Here's what this will look like. Here's what your output's supposed to look like. Up at the top, I do a Python 3, live.py, which Python 3, and I give it, in this case, an address that is meaningful on my platform, which is where I will test your code. So there you go. You should try this out with a bunch of different stuff. And so what you're seeing here is down at the bottom, that's the set of registers we give you to start, right? We said R12, 13, 14, 15. RAX, because it's a return, RBP, RBX, and RSP. Notice they're in alphabetical order, or at least a form of alphabetical order, right? It's alphanumerical order, I guess I should say. I want you to do that, and that turns out to be easy. I'll show you how to do that in just a moment. And then we step back one, and we get this, and we work our way back up through it, and you can see here XMM enters the picture, and we get up to the top, and we have all of these that we would consider to be live registers. What I want you to do then is take the set at start and remove the ones that are in this set down here, so compute the difference, this one minus this one, and that will give me a set of registers that are live at the start that omit the ones that are common and I don't care about. And so that gives me RCX, RDI, RDX, RIP. We could throw that out if we wanted to, but that's okay, we'll leave it in. And XMM0. These are the ones that I can consider to be live in this code fragment. And at the end, I take this bottom line and I subtract this top line. And when I do that, I wind up with just RAX. So let's go back to, and so we have things like this register is referenced here, it must be live. RBX comes in, RBX is probably live. Here's RDI being referenced without anything happening to it previously, probably live. What else might be live? Well, this says RCX and RDX. Let's go back. Where's RCX? Well, there's RDX. Look at that. RDX is being referenced. We haven't set it anywhere up here, so this must be a value that comes to us from our outer context. So it must be live. Here's RCX. Again, here we're referencing it. We haven't set it up here anywhere, so this value must be flowing in from outside. So what we've done here is we've really figured out this is the set of things that are provided as arguments, and this is the return. Pretty neat. Call your program live.py, and here's an example of how this will go as you work through it. So the stuff in blue is a little small program, and then the stuff in black is the set. So we start here above the return with this set down here at the bottom. Here we overwrite RAX with RCX. So we remove RAX from the set and we add RCX to it. So here's the next version of the set. We move up here and we overwrite RCX with the sum of RCX, RSI, and the carry flag. So we would throw away RCX, but then we immediately add back RCX, and we also add RSI and the flags. And so you see those two get added right here. And RCX doesn't go away because it's also an R value. Up here we decrement RCX, so RCX gets thrown away because it's overwritten, and it gets added back because it's the thing we used to override it, so no change. Okay, we keep working our way back, and we make changes all along the way until we get up here, and here's our final set. And there you go. At the end of this, we find out that REX is live. At the start, RDI and RSI are. So the first two arguments under the calling convention. We're going to ignore calls. We're going to ignore syscalls. You might give some thought to how you could handle those. Right? You could maybe do analysis of them and figure out, just like we did here, what's live at the end of them and what's live at the start, and then use that as your set. You populate over here, right? So for example, if this were called somewhere, instead of starting with this set, I would start with the live set immediately prior to the call, and by that I mean the live set immediately after the call. Sorry, immediately prior to considering the call. Remember, we're working backwards. So the live set immediately after the call, and then I would modify that based on what's up here at the top, and that would give me the result for that. But I could also do some non-trivial good stuff without doing that analysis. And what would that look like, and how would that work? Give that a little bit of thought. It's an interesting exercise, because you might want to analyze a program and you don't have access to something that you're calling, and you can still do some analysis even in that case. Here we're just going to ignore it. Some hints. You'll find Python sets useful, I bet. I'm going to guess. You don't have to use them, but I would think they'd be good to use. Up at the top, you can see an example. I've got a set called registers. I'd like it to be sorted, and the way you sort it is by calling sorted on it. I'd like it to be printed out as a comma space separated list, and there's how you do that. Comma space, join, and then the sorted registers. You might find it useful to use a map, so that down below it I have X gets the empty map, or the empty set, however you want to think about it, and then I start adding elements to it. In this case, I'd add an address, and I give it a mnemonic. And now I'd like to print that set in order. And so I call sorted on it, which is back a list of pairs. I iterate through those pairs, and I print each one out. One thing to know about these sets, you may want to stash a set away in a data structure. It's not going to work the way that you think, and it's not going to work the way that you think after I said that, right? You may think, oh, they're all going to be linked together. No, they're not. Oh, they're not going to be linked together. No, they're not. It's going to be weird. So to avoid that, you can create a shallow copy of a set before you try to stash it in a data structure. And you do that by calling copy on X. So I mentioned before a function called normreg, which takes those weird register names and converts them into a normalized register name. This is it. So up here at the top, register aliases. So here are all the common registers we want down the first column here, and for each one we give an array that contains the different names that implicate that register. Okay, and so reg name comes in, it iterates over them, it sees if it can find the name in this side of it. If it can, it returns the key, which is this first thing. If it can't, it returns the original register name, and you're good. And so that will normalize them for you. Faster ways to do this? Absolutely. A simple lookup table where all the aliases are given and they all point to the value would work just fine. I didn't feel like typing all that out, so I did this much simpler thing up here. That's it. Take care.